Okay, so I will be starting my class today. So today I will be starting with population part 3. So with this I will start presenting my screen. So yesterday, the last day, we had stopped at population growth and intrinsic rate. So when in a population, the population starts to grow, we have to understand what are the growth forms. So when there is abundant resources, that means when the resources are plentiful, the population can grow in two manners. The first is in a geometric manner and the second is in an exponential manner. I will explain what is geometric and what is exponential. So a population growing at its maximum rate grows slowly at first and then faster and faster. So population growth accelerates. First the growth is slow and then suddenly it grows fast and fast and fast. It will start growing up like this. This is how it goes. It grows up fast, first slow and then it starts to grow very fast. So this is population growth. That is the number of population people, individuals increase in that population over a span of time. So when growing at their maximum rate, that maximum means the population can't grow faster than that. Some populations grow geometrically, others exponentially. Geometrically means 2 plus 2 4 plus 2 6 plus 2 8 plus 2 10. Grows arithmetically. And let us see what are these things. And then exponentially, zoom, it goes very fast. It grows in the part of into raised to the power. It grows to in exponentially, that is very fast. For example, 2 to the power 1 is equal to 2, then 2 square equal to 4, 2 cube is equal to 8. So 2 4 8 16 32, this is a very exponential growth. So this is a very fast type of growth which is taking place. So this is how the growth takes place. Population growth takes place. I will come into details about from curves on how population growth takes place, and there are certain formulas which you will be need to remember. So populations are open and dynamic systems. So population means some people can come inside a population and people can get out from a population. So they are dynamic. So individuals are added to a population through, first is birth and immigration. So immigration means people from outside, they come inside. That is immigration. Birth means individuals are born and they are removed as a result of death and emigration. If the gain exceeds the losses, that is B plus E I is greater than D plus E. So birth plus immigration, if the sum is greater than D plus E, the population will grow in numbers. This change in population size over time can be calculated by adding birth and immigration to the original population at time t, that is nt. This is the number of individuals at time t, and subtracting the number of birth and birth, this should be death. Just remember that in this note, I'll correct it. It should be death. Number of death and emigrants to give the population at time at t plus 1, at time after say 1 day, next point of time. So n t plus 1, that is the final population after time t plus 1, that is n t plus b plus I minus b minus e. So this is the final population. So in a closed population experiencing no change of individuals, population growth will depend upon birth and growth rates. Population can be regulated by density. So if the density of a population increases a lot, then what happens? Then the population growth goes down. That is, the growth rate depends on the size of the population and how close it is to the maximum that the habitat can support. So in a particular area and habitat, there is a maximum amount which of individuals which this area can support. That is what it is saying. So as the number of population increases here, keeps on increasing, the space and resources, they become a constant, and then suddenly this maximum, the more space and resources there, the more will the population will grow, but less it is, the less it will be growing. That is, the growth rate depends on the size of the population and how close it is to the maximum that the habitat can support. For a particular set of condition, population has maximum potential for reproduction, which is its intrinsic rate of increase, that is R. So the intrinsic rate of increase, or R, is the theoretical maximum that may be reached in a given environment if the population is not resource limited. So R is the intrinsic rate of increase, that is, that for particular population, that is the maximum it can increase, that is the rate. Rate means number of people per unit time, that is maximum. For example, a human at a time cannot give more than 4 or 5. That is the maximum it can reach. A population maximum, all of them reproducing, maximum you can get is the value R. So it can be it is the basic reproductive rate. So we have a reproductive rate, that is one individual per at a time from one person. You can have only one. In fact, you can have half a person from one individual from in a population. So if a population of humans is 100, then at a time males cannot give birth. So if you assume 50 are males and 50 are females, 50 females will give birth to 50 children. That is thing. But of course, all of them, if they have twins, then it can give rise to 100. But that doesn't happen. Normally, it is said that only one person is born from one female. There are twins. They are exceptions. They are not supposed to have occurred, but they occur because of some errors. Otherwise, normally only one. So R is equal to ln, that is log of R0, that is the basic reproductive rate, by T. T is the time. So this you have to remember this. Okay. The parameter R is usually applied to a closed population where no immigration or emigration occurs. So this is in a closed population where nobody goes out or nobody comes in, this formula is being used. You have to remember it. You don't have to do sums on this particular thing. So this remember this formula and this formula. 2 marks, 1 marks, it will come from here. Now let us go to the geometric growth curve. So what happens, this is a geometric growth curve. See, it keeps on increasing. First it is slow, then suddenly it starts to grow like this. Keeps on growing. Growing geometrically. The number of flocks is a type of flower. Flocks at any point in time can be determined by using this formula. So for this geometric growth, this formula, integrated formula is used. That is nt is equal to n0 lambda to the power t. So what are this? The nt is the number or the population at some time t. N0, okay, number at some initial time 0. So t is at some time, number what was present initially, t is after some time, n0 is at first, what was the initial population, that is into lambda. Lambda is a particular value. It is the average number of offspring left by an individual during a time interval, and that is raised to the power t. So lambda basically here in this case it is 2.4177. That is the value of lambda over here. So a population that is increasing at its intrinsic rate will undergo a geometric increase in a population number and will follow the characteristic geometric curve. So this is a geometric curve when it is if the population does not run out of resources, that is food and space and all. If it doesn't run, it will keep on rising exponentially using this formula to the power t. So here lambda is 2.4177. So it will keep on increasing. Slowly it will keep on. This is known as geometric growth curve. The next is exponential growth curve, that is the J-shaped curve. You have to remember this formula. So this is a differential formula, you know, this is the differential formula. If you integrate it, one second, if you integrate this particular formula, if you integrate this, you are supposed to get this value. Next day I will explain in details how you can derive this formula by integrating from this formula. So this is what this geometric growth you are seeing. This is a J-shaped curve. This is a J-shaped curve which is taking place. So exponential growth curve. So you can see that this is exponential growth curve. This type of growth curve is this, and you remember this formula. dN by dt is rate of change of population per unit time, that is equal to R equals to the per capita rate of increase times number of individuals, that is the increase per capital rate of increase, and N is the number of individuals. So follow this formula. So this is X. Then you have the next type of growth curve or S-shaped curve. So basically what you have to learn is J-shaped curve. You can call this as exponential or geometric, and you have the S-shaped curve, that is the sigmoidal curve. In the sigmoidal curve, you have to remember this is the formula for this curve, and essentially you see a slow growth, then an exponential growth take place, and then resources start to become, at higher density resources become limited and the growth slows down. This is how it takes place. This is a sigmoidal curve, and this is the formula for sigmoidal curve. All these are basically very easy, don't have to bother yourself with the mathematics. Just remember this formula. Remember this formula, that is this one, and then you have an integration to this formula. You see, this is also an geometrical exponential growth curve. This S-shaped and J-shaped curve I will also go in detail from another book known as Odum. On the next day I will show it from Odum and the integration part of this population growth curve. Next we have density independent and density dependent mechanism of population regulation. Now what are these? In low diversity physically stressed ecosystem, or in ecosystem subjected to irregular or unpredictable perturbation means population size tends to be mainly influenced by physical factors such as water, weather, water currents, chemicals, and natural calamities and population. In high diversity ecosystem, benign environments, periodic physical stress such as storms, fires, populations tends to be biologically controlled. So, what do you mean by density dependent? Density dependent factors are factors which are dependent on the density, and a density independent, that is, say a population increases or a population decreases. A population is increasing here and a population is decreasing here. There are two ways by which, one is density dependent and the other is density independent factors. So what is a density dependent factor? Density dependent factor there is the factors which are dependent on the density. So the more the number of individuals in an area, the density increases and the population starts to fall. Another reason why the population can fall is that there is a fire, storm, calamity, and all these factors take place, and that this factor it is density dependent on the density of the not dependent on the density. So a fire comes and many people die, coronavirus comes, many people die, and all these things these are controlling the population. So the population starts to fall down. So this is density dependent or intrinsic factors such as competition, however, tend to maintain a population in a stable pulsing state or hasten the return to such a level. And density independent environmental factors have a greater role in physically stressed ecosystems. So density independent, when there are a lot of people living in very close together, they start competing with each other for resources, and because of that some people die out. They don't get enough food or enough medication and they die. Some people because of infighting they die out. By this the population decreases. And in density independent, you are talking about the physical factors. You will find all of these things in this. It's written clearly in this. Read them slowly. I'll send this note. Then you have one known as the R selection. So like this rats, they have lots of pups, but all of them, only one or two of them will survive, the rest will die. This type of survival is known as the R selection, which organisms with smaller bodies tend to have these R selections. Dogs also have these R selection, cats also have R selection, but in the case of humans it is K selection. It is known as K selection. Then we have competitive exclusion principle, or it is also known as Gauss's law of competitive exclusion. In this, what happens? There is one simple statement: complete competitors cannot coexist. That means complete states that two species aren't able to coexist in at a constant population values, competing for the same resources. For example, lions and tigers, they cannot live in the same place. In one forest, you will never find lions and tigers together, because they are competing for the same resource, that is the deer. So they cannot compete for this. This is Gauss's competitive exclusion principle. Complete competitors cannot coexist. What do you mean by a complete competitor? A complete competitor is a competitor who competes for the same resource. For example, lion and tiger will compete for a deer, so they will not be able to live in the same place. They will be able to live only under one condition, that is, it's not over here, but that is niche segregation. When niche segregation takes place, I will explain that in my next class. It is known as niche segregation. Now, what is niche segregation? In a pond, say imagine a pond, there are three species of fish which we know. One is Labiorohita, rohu, Katla, that is Katla fish. Then you have Sirena mrigala, that is the mrigal fish. So you have these three থাকে, mrigal niche থাকে. ঠিক আছে? হ্যালো, আচ্ছা, ওপরে রুই থাকে, ওটা আমি আমার কাছে আছে, এই নোটটাতে খুঁজে পাচ্ছি না কেন জানি না, আমি বোধহয় এটার মডিফাইড ভার্সন। সো দিস ইউ হ্যাভ টু রিড দিস এক্সপেরিমেন্টস with Paramecium caudatum and Paramecium aurelia. In a same culture, Paramecium aurelia and Paramecium caudatum, they have the same bacteria as their food. So they see that this Paramecium aurelia, they win the battle and increase, and the population of caudatum goes down. So they cannot coexist in the same place. This is the experiment. Then this is the Lotka-Volterra equation. This I have to explain to you in details in the next class. The next class will include Lotka-Volterra. It will include your J-shaped and S-shaped curve, and how the differential and integral equations. So these two will be in the next class. These are also things which you did not read. Yes, I can understand why I am not able to find this. This is a different note. Okay, so tomorrow I will talk about, not tomorrow, the next class. Today is Wednesday, so I take your classes on Monday, right? So on Monday I will take my next class. With this I stop my lecture, but just hold on, don't leave. I have got one more thing, a few things to show you. Just hold on, don't leave the class. AG, where is that AG note gone? Okay, important backup. This is my note actually. Here, exponential geometric curve. This is the note. It's written perfectly. I have removed that from there. This is my note. Therefore, Lotka-Volterra model. Okay, so this is what I wanted to explain. What the term? Just hold on. And disease. So this is the maximum reproductive capacity of an organism under optimal environmental condition. That is the definition of biotic potential. And once, just hold on some more. I have to explain one more thing. Where is Odum? Just hold on. So if you see this, population increases and then gradually it comes. So this is the carrying capacity. This is the maximum. So carrying capacity can be actually defined as the maximum carrying capacity of individuals in of a population. So as population grows in an area, a population may experience the effects of increased density. In a given area, maximum population size of the species that the environment can sustain is known as the carrying capacity. So, and this carrying capacity is determined by the amount of available resources. So with this, do you people have got any questions? আচ্ছা কোয়েশ্চেন প্রীতদীপ, তোমার আওয়াজটা শোনা যাচ্ছে নেই না?
No, sir.
কালকে আমি আসলে জে শেপড আর এস শেপড কার্ভটা তোমাদের ভালো করে বোঝাবো, আজকে ইন্ট্রোডিউস করে দিলাম জিনিসটা। ঠিক আছে, সোহম, এনি কোয়েশ্চেন্স? Nisab, any questions?
No, sir.
Okay. So Neha, no questions also. Okay. Neha, questions?
No, sir.
No, sir.
ठीक আছে, okay, okay. Then I end my class today here. On Monday we will meet. But tomorrow we will meet in the college class.
Okay, sir.
স্যার
হ্যাঁ বলো, yes, yes. বলো।
স্যার বলছিলাম যে গ্যাসের থিওরেম ছিল যে একটা ইকোলজিক্যাল নিচে একসাথে দুটো কোনো স্পিসিস একসাথে সার্ভাইভ করতে পারে না।
কমপ্লিট
Gauss's theorem যেটা
কম্পিটিটরস,
বললো।
কমপ্লিট কম্পিটিটরস না হলে সার্ভাইভ করতে পারে না।
কমপ্লিট টেস্ট বলে।
Yeah,
আচ্ছা,
what
স্যার,
do you
ওটাই
mean by complete competitor? Complete competitors, like it may not be, it can be also be the same species, but we are talking about two species over here. Complete competitors means like lion and tiger, both of them they eat the deer, right? So both of them, out of them only one will survive. For example, in our Bengal, lion went away from Bengal. In first, in the forests of Bengal, there were lions also, but the Royal Bengal tiger was more suitable, more adapted to this habitat. So it won the battle. So in Bengal, you will not find lions. In Bengal, you will find tigers. You'll find it in the Himalayan tigers also. You will find the tigers in Sundarbans also, the Royal Bengal tiger and other tigers. But if you go to Gujarat, in the Gir forest, the tigers have lost the battle over there. Over there it's the lion, because it's more drier. Lions are more suited for grasslands and dry populations. So the lions, they got restricted over there. But in India there are lions. Mostly they are tigers. Only in Gir you will find lions, because India has got a lion capital. So that is good proof that lions existed in all over India at one time point, but they got overpowered by the tigers. Similarly, in Australia, a very interesting thing which happened was that its native carnivore was the marsupial wolf. It's a marsupial. Marsupials, they've got they have the like kangaroos, they have pouch in which their young ones develop. So the marsupial wolf was the endemic population over in population in Australia. But then from the mainland, all people came inside and they colonized, and they brought with them a famous fighting dog known as the dingo. So dingo was the dingo dog. It was also a fierce competitor. It was like a wolf. It had a wolf-like characteristics, this species of dingo. So the dingo was much more adapted and much more powerful. So gradually the marsupial wolf population just fell down rapidly, and so they went to almost to the brink of extinction. So they could not compete with the dingoes. Now they are kept in zoos and protection and all these things. But essentially they were the main carnivore over there. They just lost out the battle. Similarly, the experiment can be it was done in test tube also. You can see Gauss's principle, that Paramecium aurelia and Paramecium caudatum. Different Paramecium aurelia is the Paramecium which has got a golden color. Whenever it grows in a medium, the medium has a light golden shade. And caudatum means in these Paramecium cultures they have got a tuft of cilia on their tail, a long tuft of cilia. Therefore, it's known as caudatum. So in the caudal region they have this cilia. So these two, but basically both of them are Paramecium. But when both of them are grown in a Paramecium culture, hay culture, the population of Aurelia grows rise and Caudatum falls below. So because Caudatum and Aurelia, they are complete competitors. They compete for the same resource. So one of them survives, another dies out. This is Gauss law. And one more thing which I have to teach you is the Lotka-Volterra model, and that is the predator-prey relationship. Briefly, I can tell you what happens in this Lotka-Volterra model is that the number of predators or the number of tigers in Sundarban is determined by the number of deers. More the number of predators, the more the number of prey. More the number of prey, more the predators. If the predator population increases, then you can bet on your life that the prey population has also increased. If the prey falls down, the predator number also falls. So the predator-prey relationship, it shows. It is tightly linked. It's shown by a mathematical equation by Lotka and Volterra. They did a study with lynx and hare. Lynx is like a wolf and fox, and the number of lynx population and the number of hare population. Let's see if I can show you on the internet this particular picture.
তার মানে দুটো
তার মানে বলো বলো
স্পিসিস যেখানে একজনই মানে একটা থেকেই দুটো স্পিসিস যেখানে একটি প্রজাতিকে খাদ্য হিসেবে গ্রহণ করে তাদের মধ্যে
এক্স্যাক্টলি হ্যাঁ
কম্পিটিশনের ক্ষেত্রে
নট অনলি খাদ্য, একটা মানে জায়গারও ব্যাপার হতে পারে, সেম স্পেস। ওটা মানে কখন খাদ্য কেন, ইট ক্যান বি অলসো ফর আদার থিংস ফ্রম ফুড অলসো, ইট ক্যান বি স্পেস, ইট ক্যান বি সানলাইট, ইট ক্যান বি হ্যাঁ।
দেন ফরেনের অনেক কান্ট্রি থাকে যেখানে একসাথে গরু, ছাগল, ভেড়া এইসবের বড় বড় ফার্ম থাকে যেখানে একসাথে দুধের উৎপাদন হয়।
Resources are not limited over there. In a farm you keep on giving them. In a farm you keep on giving them food, extra food for this. But normally all of them they are not resources limited হলেই একটা কমে যাবে। জঞ্জালের বিনে দেখো না, তোমার ছাগলগুলো আসতে পারে পারে না, গরুগুলো এসে খেয়ে যায়। সো
অনেক ক্ষেত্রে তো মানে সাপ্লাই তো করেও না, অনেক ক্ষেত্রে চারণভূমি দিয়ে দেয়, যেখানে চলতে ছেড়ে দেয়, সেক্ষেত্রেও কি একে অপরের মধ্যে কম্পিটিশন হবে না?
when the resources start to become limited, then immediately you will find the problems. একজন বের করে দেবে আরেকজনকে। If they are complete, গরু আর ছাগল, if you have both sheep, if you have goat as well as cow in a field, if the resources are limited, you will see for after some days the number of sheep will not come over in that region, or the number of goats will reduce. It will be only cows who are there. So this is the prey population in blue. It's increasing and decreasing. So as this is increasing, the predator population is also increasing. As it is decreasing, even this is also decreasing. So this is how the predator and prey relationship exists. They showed by this this is lynx, a type of fox, and this is hare, a rabbit. So the population of rabbit increases, population of lynx also increases. It decreases, that also decreases, again increases. So they are linked. যত predator থাকবে তত prey ও থাকবে in the same ratio. The ratio will remain the same. This is the essence of Lotka-Volterra model, and essentially you have to remember the formula. ঠিক আছে, am I clear?
Yes sir.
Okay, then I end my class over here today.